very happy and very fortunate to introduce Dr. Valentin Rime, who's spending some time here at the University of Sydney. So he'll be back mid-January. So you know, if you've got any questions about the talk, come and have a coffee with Valentin and have lunch with us. So Dr. Valentin Rime is a geologist in the University of Freiburg. I hope I pronounced that right. Specializing in tectonic and sedimentological studies within rift environments. His research primarily focuses on the Afar and Danakil regions, key sites for studying continental rifting that transitions into oceanic spreading, which of course is very important for plate tectonics. His work includes analyzing the geological and climatic evolution of these areas, such as investigating marine incursions and salt deposits, which offer insights into both ancient and current rifting processes. He also employs field studies, remote sensing, core sampling to better understand these complex geological processes. So wonderful to have you here, Valentin. We miss you here at Sydney. I know you're currently in Switzerland. So hopefully you've got a good coffee there with you. I'll hand over to you, and thanks again for sharing with us.
Yeah, thank you, Sabine. So I will share my screen with you. Is it okay? Do you see it correctly?
Fantastic. We can hear you.
Okay, perfect. Great. Okay, so we'll start. Thank you very much for inviting me for this talk. And what I want to discuss today is some of the results of a big project that is a collaboration between the universities of Fribourg in Switzerland and the University of Addis Ababa. So it's a long-term project that started in 2013 to do fieldwork in the Afar Depression and more specifically in the Danakil Depression in the north, you will see. And this project is mainly about sedimentology, but then when I went there, I was like, oh, but there is fantastic tectonics, and we have to work a little bit on the tectonics also. And that's the part I want to discuss now today with you about rifting, breakup, and the transition to drifting, and some of the lessons that we can learn from the Afar Depression. So I will first start by discussing very quickly the current model of passive margin formation here for the ones of you who might not be specialists in rifting and passive margins. Then we'll look at the Afar region as a whole, and then look at two sub-regions, the central Afar and the northern Afar, the Danakil Depression, which are two different regions which have different characteristics you're going to see, and then some take-home messages. So the first part, a bit of a wrap-up of the current model of passive margins. And typically in textbooks, passive margins are classified between two end members, the magma poor and the magma rich margins. And to make it very simple, magma poor margins are characterized by mantle exhumation, and most of the time they have seaward dipping faults. Magma rich margins, they are characterized by seaward dipping reflectors. We're going to talk about this more in the presentation. And usually they have continental dipping fault. And if you look at the global map of the distribution of this seaward dipping reflector in dark gray and exhumed mantle in green, there's also intermediate margins presented here, and the large igneous provinces. You can see that sometimes large igneous provinces, they fit with the magma-rich margins. For example, the North Atlantic, where you have North Atlantic igneous province, and there it's a very typical magma-rich margin. And then the Iberia, Newfoundland margin, you're further away from hotspots, and there it's really the textbook example for magma poor margin with mantle exhumation. It also works well offshore the west coast of India, Deccan traps, and then the magma-rich margin. But there are some places where this model is not working as well, like the northern part of the South Atlantic. You're very close to the Tristan hotspot, the Parana flood basalts, but it's an intermediate margin. You not have seaward dipping reflector in the northern part of the South Atlantic. In the southern part of the South Atlantic, there it's typical seaward dipping reflector. Then you have the Gulf of Aden, very close to the Afar hotspot, but it's an intermediate margin, and even sometimes you even have mantle exhumation. And then you have some special things. For example, near the Rio Grande rise, so along the hotspot track, the oceanic crust is not any thicker than the 6 to 8 kilometer of a normal oceanic crust. Or in the Gulf of Mexico, you have a cross-section that show seaward dipping reflector and exhumed mantle along the same cross-section. Same in the equatorial Atlantic. So it seems that this classification between magma rich and magma poor does not really describe perfectly all the variety that you can have. And you have this very interesting paper by Pauline Chenin, who proposed in 2023 that this margin should rather be described with not only with the volume of magma, so whether it's magma rich, a lot of magma, or magma poor, but rather the timing of melt and placement, or also the timing of melt and placement, because you can have a lot of melt coming very late, and then you would still have mantle exhumation, or you can have only a little bit of magma but coming very early, and then you would see all this magma and you would think, oh, that's a magma rich, but actually that would only be a magma early, maybe you can say. So to sum up, it's complex and we don't understand the full variety that is out there in our oceans. And the question of this presentation is, what can we learn from the Afar region about this topic? And so we go now to part 2 about the Afar region, so the whole region. And this region is interesting because, as you can see from this picture from the International Space Station, a big part of it is situated above sea level. And that means that you can go there, you can do field work, you can do remote sensing with satellite images, and this passive margin is not buried under 2 kilometers of water and then 3 more kilometers of post-rift sediments. So it's a very good opportunity to study this mechanism on site. So where it is, it's situated here. It's part of the Afro-Arabian rift system. And if we now look at the kinematics of the plates in the region, it's a triple junction between the Red Sea rift, the Gulf of Aden rift, and the East African rift system. But it's actually 2 different systems that interact with each other, because you have the Arabian plate that is drifting northward at approximately 20 millimeters per year in the region of the Afar. And then the Somalia plate that is moving away from the Nubian plate, then it's moving much slower. It's only 5 millimeters per year, and it started later on. So it's not symmetrical across the 3 branches of the triple junction. It's rather 2 systems that are interacting, but that are a bit different. You can also see that the topography is higher in this Afar region. That's dynamic topography because we have a hotspot there, the Afar hotspot, that goes down to the African superplume rooted at the core mantle boundary. And this led to the eruption of the Ethiopian large igneous province approximately 30 million years ago, that you can see here in this light red colors across Ethiopia and Yemen, up to 1.8 kilometers of basaltic flows that were deposited prior to rifting. Now we're gonna zoom a bit more on really the Afar region here. And I told you it's a triple junction, but actually it's a bit more complex. The tectonic structure is a bit more complex because you have this Arata microplate in the middle. And so that makes a real kind of a relay structure between the Afar rift and the Red Sea rift. So it's a little bit more complex. And this region has often been used as a model for rift evolution. For example, there is this famous paper by Hayward and Ebinger, and they propose that the northern main Ethiopian rift, part of the East African rift system, would represent an early or mid-advanced rift morphology, and then you would have more advanced situation somewhere here, and the most advanced stage of rifting just here in the northern part, in the Danakil Depression, in northern Afar. And that makes some sense because in the north there, you have the thinnest crust of the whole system, and you have a volcanic range with no crustal contamination. So probably we have continental breakup here. But this model does not work when you look at the kinematic of the region, because you see the counterclockwise rotation of this Arata microplate here. It's rotating counterclockwise, and we know it's not just a recent Pleistocene feature, it's a long-term feature. And with this rotation, this means that the rifting is propagating towards the north. And so you have much less extension in the north, approximately 60 kilometers, and much more in the south, 260 kilometers of extension in the south. So why would the north represent a more advanced stage of rifting when it experienced much less extension than the south? And so we have to look at which part is not fitting, and the part that is not fitting is the southern part, the central Afar part, because if you look at here, in the Red Sea, you have the same amount of extension, 260 kilometers of extension, but there you have tens of kilometers of oceanic crust that have been produced, and we don't have this at all in the central Afar. So we're now going to zoom on this part, the central Afar, and look at what is not working there. And by the way, if you're interested in fault patterns, that's really the place to go to. If you just go to Google us, you see superb fault patterns just because it's a desert, so there's no vegetation, so you can see these beautiful fault patterns there. Okay, so the problem is central Afar experienced the most extension, but that's the only place of the Red Sea Gulf of Aden system which has no oceanic crust, no crustal breakup. You see here, that's the limit of the continent-ocean boundary. And you see central Afar is the only place of the system where we don't have normal oceanic crust. Why? Why is the crust so thick? It's the thickest crust of the whole system. And why don't we have this nice seawall dipping reflector structure? We're going to come back on the structure. And our hypothesis is that central Afar is not a conventional magma-rich margin, but an incipient oceanic plateau. And before discussing the specifics of central Afar, we have to discuss a bit what is an oceanic plateau. And like often in geosciences, there's no clear definition. Often it's only considered within oceanic plateau are only considered within the framework of the study of large igneous provinces, and for the fact that they are large igneous provinces, but not for the fact that there are interesting features as such. And the naming of the different feature across the oceans or the nomenclature between the publication is not consistent, and we're gonna see this. But there are a few features here. I will only show Atlantic and Indian Ocean. There are a few features that almost all authors agree are oceanic plateau. These are, for example, the Rio Grande Rise in the South Atlantic here, the Northeast Georgia Rise, Maud Rise, Del Cano Rise, and Kerguelen Plateau. Okay, if we now look at a few definitions, here, for example, present oceanic plateau as just over-thickened oceanic crust. So they're just thick oceanic crust. And that is challenged a bit by the discovery in the last years of continental material in several of these oceanic plateaux. We're going to come back on this, usually because they found either gneisses or zircons that are much older than the oceanic crust, so indicating that you have something old continental embedded somewhere in the plateau. Then we have a definition by Coffin and Eldorm that is a bit more about the morphology. An oceanic plateau for them is something broad, rising above the surrounding seafloor with mafic volcanism and higher crustal thickness. And this is interesting. And in this paper, they also define two other features of large igneous province that I want to mention here because they're going to be important for the next part of the presentation. These are submarine ridges, and basically they are the same as oceanic plateau, but just they are elongated. For example, the Broken Ridge they define as a submarine ridge, or the Chagos-Lagadive ridge. And they also define volcanic passive margins, and these are rifted edges of continents with a lot of volcanism. And for example, the Seychelles would be a volcanic passive margin for them. And then we have Brian and Ast that say that a large igneous province must have a large volume and a short duration. So everything that was a long-lived structure like Iceland, then it's not considered as an oceanic plateau for them because it's not a large igneous province, because it's a long-term feature. And so you will see that then it's not consistent across the publication if you look at the different feature. For example, the Greenland, Iceland, Faroe Ridge here in Iceland. Some say it's an oceanic plateau, some say it's between an oceanic plateau and a submarine ridge, and some say it's not a large igneous province. The Broken Ridge here in the Indian Ocean, some say it's an oceanic plateau, some say it's a submarine ridge. Mascarene Plateau, Indian Ocean also. Some say it's an oceanic plateau, some say it's not, some say it's a volcanic rifted margin. The Chagos-Lagadive Ridge, here, Indian Ocean also. Nobody says it's an oceanic plateau, some say it's a submarine ridge, some say it's a volcanic rifted margins. And so it's not consistent across the different publication. And so we had to nail it down, and we said, okay, we'll just consider everything that is big and elevated above the surrounding oceanic basins. And of course, if we wanted to compare this with the Afar, it made no sense to compare, for example, the Ontong Java Plateau or the Shatsky Rise or the Azores Plateau, or the Sierra Leone rise, or the Conrad rise to the afar, because these oceanic plateaux, they were never involved in the rifting. They were never in contact with a continental crust. And so that makes no sense to compare them with them. So we classified oceanic plateau in two different categories. And the first one is oceanic magmatic plateau that we define as developed exclusively on oceanic crust with no evidence for ever having been connected to a continent. And this usually we know pretty well with plate tectonic construction of Sabian, for example. We know pretty well whether they were connected to a continent where they started forming, and this we can quite easily define. And then the other type would be what we call rifted oceanic magmatic plateau. And these ones, they started forming during the rifting stage, and they were originally connected to a continent and a continent flood basalt province. And this usually, you know where the continent flood basalt province are. And so we divided these two, and the examples of rifted oceanic magmatic plateau, what we call this, would be, for example, Iceland, Alpha Mendeleev rise in the Arctic Ocean, Rio Grande rise, Northeast Georgia rise, Moat rise, and Agula Plateau that were once all together, Del Cano rise, Madagascar Ridge, and maybe Mozambique Ridge that were once all together, Ascarin Plateau, maybe Chagos Lagadive Ridge, although it's not the shape of an oceanic plateau. We'll come back to this. Kerguelen and Broken Ridge, Naturalist Plateau, Zenith Wallaby Plateau, and we think the Afar is an initial stage of all of these things. So what we did is that we compared a few characteristics of this rifted oceanic magmatic plateau with the Afar. We looked at crustal thickness, timing of magmatism, presence of continental material and tectonic structure, and we'll go through this information. Sometimes there's not a lot of information for this feature because they're so far offshore. And first, if we look at the crustal thickness here, you can compare the Afar region with Iceland, and you can see that the crust is thicker than any surrounding margin. For example, here in central Afar, you can see the crustal cross-section area, so the volume of the crust is much higher than anywhere else along the same margin. Same for Iceland, it's much higher. And so the crust is thicker than what you would expect. So there has been addition to the crust. And of course, we interpret this to represent magmatic addition to the crust. And it corresponds to quite a lot of material, approximately 3 times more magma than the normal 6 to 8 kilometer oceanic crust. So that means that we have a lot of magma in this rifted oceanic plateau, which is not a surprise. Timing of magmatism, by definition, it's always linked to continental flood basalts. And so the eruption started prior to rifting, or at least prior to breakup. And so the magmatism is not only voluminous, but it's also early. And then one very interesting feature is continental material. In a lot of these oceanic plateau, continental material has been found, and sometimes dragged very far in the offshore realm, like in the Rio Grande rise, Northeast Georgia rise, Agula Plateau, Mozambique Ridge, in the Kerguelen, Naturalist Plateau, Broken Ridge, Mascarene Plateau in the middle of the Indian Ocean, Alpha Mendeleev rise also, and more recently in Iceland. This is not published yet, but one of our co-author, they found zircons, Paleozoic zircons in Iceland, and this together with geophysical indication, they think that this shows that there is some continental material maybe under Iceland. Let's now look at the structure. So I will show you 2 cross sections through Central Afar and Iceland, and I will zoom a bit on it. And you see that it's not this typical seaward dipping reflector with just this symmetrical structure, but we have multiple synclinal structures. You have the seaward dipping reflector on the margins towards the continent, but then you have all these synclinal structures, and they represent multiple rift jumps. The rifts are jumping all the time in this oceanic plateau. You also have overlapping rift segments. Maybe you see this a bit better on the geological map in Iceland, but also in Afar, we talked about this relay structure. So the rifts are all overlapping. And we think that this can explain the isolation of continental material far offshore, because if you always have the rift that are jumping, you're cutting pieces of continental material that you're then chopping up in small pieces and that you can drag very far offshore. And possibly it might also be linked to the formation of microcontinents, because if you look at the distribution of microcontinents, for example, in the Jan Mayen microcontinent, Sao Paulo High has been considered a microcontinent, the Seychelles microcontinent, Ellenbank has been described as a microcontinent, and the Danakil block in the Afar is considered a microcontinent. They are all close to these oceanic plateau, not necessarily embedded within the oceanic plateau, but close to them. And we think this is also linked to this rift jump, so that there might be also a link with the microcontinents here. And so this is our model for the formation of a rifted oceanic magmatic plateau, a sketch of it compared to conventional magma-rich margin to make a bit of the difference. And all of these figures here, they are all balanced. So the surface, the area of the crustal material in gray will stay constant from one stage to the other. And the A to D on the left, rifted oceanic magmatic plateau, they represent what we know about the evolution of the Afar. So you would start with continental flood basalt before the rifting, so already a lot of magmatism very early on. And then you would start rifting, but you would add so much magmatic material to the crust that you would add something that we call a magma compensated thinning. So you would not thin the crust as much as you would in a normal margin because you add so much material on top and inside and at the base of the crust. And then the rift would jump, so that would slowly isolate pieces of continental material far offshore. And that would be the present day situation of Central Afar. And then if you can imagine, we don't have good information about where there might be continental material in the Iceland, but just with balancing, you can see that even with 1,200 kilometers of extension, you can still imagine having pieces of continental material dragged very far offshore by this multiple rift jump and distributed extension. Conversely, if you look at a conventional magma-rich margin, a bit simplified, you might have a little bit of volcanism also before rifting, but not too much. But then when you start the rifting, you don't have as much magmatic addition to the crust, and so you would thin much faster, and that would be, for example, the equivalent of the Danakil depression. And then very early on, you would concentrate both the extension and the production of magmatic material to one point, and that would start forming oceanic crust. That and the continental material would not be modified anymore. And you can see that here we have exactly the same amount of extension, but two very different structures. So we think that, like the Central Afar, is something different. There is some differences compared to conventional magma-rich margin. And then we thought about the common cause, what could cause this structure. And we think that hotspots are a good candidate to explain this, because they can explain the most important characteristic that we looked at: the voluminous magmatism, the early onset of magmatism, and they can also explain rift jumps. There are several theoretical and numerical modeling studies that show that rifting about hot and buoyant mantle can foster rift and ridge jump. So a few discussion points on this. The first one is that if we think that this model is maybe not too wrong, then rifted oceanic magmatic plateau could be considered as extreme types of passive margins. They're not real continents, but they are neither true Penrose like oceanic crust. There's something in between. They are between a continent and a normal oceanic crust, both in the sense of structure, composition, but also spatially. And sometimes the machine stops, for example, here, and then you form true Penrose like oceanic crust. And so for me, something that is between a true continent and normal oceanic crust might be called a passive margin. So they might be an extreme type. There's also a case here where you have, in the end, you have normal oceanic crust, but it would be magma ultra rich and hyper extended. And if we come back to this sketch of Pauline Chenin, then it would be something here. It would be very early onset of magmatism, and super high volume of magma emplacement, so magma ultra rich margin. And it's also bridging the gap between three types of large igneous province: volcanic rifted margin and oceanic plateau, because some oceanic plateaus, not all, but some, would be similar to rifted volcanic rifted margins, so magma rich margins. But at the same time, some volcanic rifted margins, they are future oceanic plateaus. So maybe these two terms, they are not mutually exclusive, and they can be both. The structure can be both. And I want to make a small point about submarine ridges that we discussed before. For example, Chagos-Lagadav Ridge is never considered an oceanic plateau because it's so elongated, but I don't see why it should be classified as something else as the Mascarene Plateau, which they were connected together before. And I think that for this, what they call submarine ridges, the processes and the mechanism formation might be also similar. And that might also apply to the Walvis Ridge, for example. Another consequence is that Central Alpha might not reach normal oceanic spreading anytime soon, because if it evolves like Iceland, then we might have tens of millions of years until the effect of the hotspot is lower and you can have normal oceanic crust, even though the Red Sea Gulf of Aden system will probably never evolve into hundreds of kilometers of extension. Okay, we'll now jump to the fourth part, to the Danakil Depression. And the Danakil Depression, so until now we discussed about the Central Afar, and now we'll look at the Danakil Depression here in the north, and you will see that the structure is very different. You have less old magmatic material, so the continental flood basalt. You have some, but the thickness is less important, less extensive, but you have a lot of recent volcanic material. And if we look at the Danakil Depression here, you can see this is called the Ertale Range. And here I will do a small bracket because you are geologists and all geologists find volcanoes sexy. So it's out of topic, but I wanted to show you a few pictures because I like them. So the Ertale volcano is here on the arrow. You can see on the satellite image, you can even see the plume. And this volcano is famous because since the 70s, there was a permanent lava lake. And that's a picture from 2015 from my team. And I came here for the first time in 2019, and in 2017, there was a big eruption that drained all the lake for the first time. And now the eruptions are on the side. So when I came here in that's a picture from 2020, there's no lava lake anymore, but all the lavas, all the beautiful Pahoehoe lava that you see on the side of the crater, they are from the 2017 eruption. So you have the impression when you look at this picture that it just froze minutes ago. But there's even a more sexy volcano in the Danakil Depression. It's the Dal volcano up there. And it's very special because the magmatic material does not reach the surface. And there are a lot of evaporites there. And so the magmatic fluids, they dissolve the salt and you have a salt volcano. And that makes beautiful colors. And it's a very special place because these pools, they have temperature higher than 100 degrees, pH of something like -2, so hyper acidic. When my team first went there, they measured the pH and they thought, oh, our instrument is broken, it's not possible. But then in literature, it was published with the same value. So it's hypersaline, hyperacidic, hyper warm, and the biologists love this place to study the extreme of life and the limits of life because of these extreme conditions. And here's a model of it. You can, if you're interested, you can read this publication with the intrusions below. There is, for example, a dike intrusion that was measured in 2004, dissolving the evaporites and coming on top. And we also very recently published a paper about the evaporites, not much about the Dallol volcano, but the evaporites that are evaporation of seawater that enter the basin. That's the sedimentology part of my PhD. And that was a bracket that has nothing to do with the tectonics, but I thought it was super cool images and I thought you were maybe happy to see this. Okay, coming back on our topic, the tectonics, we had also access to seismic images in the Danakil Basin, and they look like so. If you look at the southern part, you see this beautiful seawall dipping reflector with reflectors dipping toward the central part of the basin with this fan shape. So we have a seawall dipping reflector structure. Here is the detail of one. And seawall dipping reflectors, they are often observed on seismic images. For example, this is one beautiful image from the South Atlantic. And they are diagnostic for magma-rich margin. And remember, that's a diagnostic observation to say it's magma-rich margin. There are several models. They are a bit different. For example, that's a model from offshore Norway and Greenland. So in the North Atlantic, that's something how it would look like in the South Atlantic. And they are thought to be formed either by faulting here, close to the continent on continental crust, or by isostatic loading here a bit further oceanwards. But the problem is that they are rarely drilled because they are most of the time below water, post-rift sediment, and then syn-rift sediment. And so the lithology has been systematically interpreted based on the seminal work of Planck and colleagues in 2000. And they related the different seismic phases with different volcanic phases. And if we look at our cross-section, we think it represents inner or type 1 seawall dipping reflector, so bound by fault and lying on continental basement. And according to the paper of Planck, that would mean that they are made of flood basalts. But the good thing about the Danakil depression is that you can go to the field, and all these reflectors are truncated, and so you can go there and see what the lithology here. And I will show you a picture from here. That's how a seawall dipping reflector looks like from the surface. Seawall dipping reflector that are still forming nowadays. And now if you zoom a bit more, you see this. It's a lot of conglomerates, sand, some silts, but not a lot of magma. And there are two long logs that have been done of several hundred meters, and they show that actually the magmatic material forms less than 30% of the content of this seawall dipping reflector. So that's a big change from what we thought previously based on studies offshore Norway and Greenland. Actually, they might not be always that much magma in this seawall dipping reflector. And that's interesting for this question of what is a magma-rich margin. And so that would mean that maybe there's not that much magma there, but it started early. And so a few discussion points, we can say that at least we have at least one example of seawall dipping reflector that are not magmatic. There are also some indication in the South Atlantic, for example, the gravimetry data, they are not fitting very well with a purely basaltic seawall dipping reflectors. And if all seawall dipping reflectors are not magmatic, it means that seawall dipping reflectors are a structure, but not necessarily diagnostic of a composition. And that has implication for what is a magma-rich margin. And then what we call a magma-rich margin with a structure might not be that magma-rich. And so that's a signal for you. Be careful when interpreting seawall dipping reflector only based on seismic. You cannot be 100% sure about the composition. Okay, and I will end up with a few take-home messages. So the question we had is, what can we learn from the Afar region? We learned something about oceanic plateau, and we propose here a new model, and we can discuss later on if you think it's a good model or not, and that some oceanic plateau might represent extreme type of passive margin rather than simply thickened oceanic crust, that the magma-rich to magma-poor classification for a passive margin is an imperfect way to describe this passive margins. Of course, the volume of magma is important, but we've seen also here that the magma ultra-rich margins have been a bit forgotten by this classification, and that there are other factors that are important, like the timing of magmatism or the structure. And usually they are linked together. If you have a lot of magma, it starts early and you have the seawall dipping reflector, but it must not be the case all the time. And then last point is that the Afar depression is very interesting to study this late rifting stage. And even though it's not easy to go and do fieldwork there, I think there should be more studies done in this place because you can learn a lot about these processes and the interaction with plumes. And with this, I thank you for your attention.
Amazing stuff, Valentin. That was brilliant. I have lots of questions, but I wanted to actually open it up to anyone else. Are there any questions? Some incredible footage and pictures there you've got. That's for sure. Okay, look, I'll get started.
Ask a question.
Oh, Chris, yes, please go for it.
So, they've always spoken about seaward dipping reflectors. If there's no drill information to tell you what's in those reflectors, why did they interpret them as basalts?
Actually, there are a few drillings. There are a few ones offshore Norway and Greenland, but they don't reach very, very deep. And that's the only thing they had in the 2000. And that's why they defined that there were a few drillings. And in the past, maybe in the past 2 years, there have been an IODP drilling campaign, again, offshore Norway. And now they have new data there. And again, they show that it's almost I don't know, maybe 95% or 98% basaltic flow. And that means that this model that was proposed is completely correct for the Norwegian margin, but might not be true for everywhere. But they had a few drillings, but just a few, and a few also outcrops on the west coast of Greenland. They have an analog, an outcrop analog, and there it's also only lava flows. So they have a few, and they based themselves on this. And then because there were no new data, then everybody interpreted this based on this few case study. And now we bring another one. There's also a new study in the southern Red Sea that showed that maybe there also we see seawater dipping reflector, and there might be quite a lot of sediments in there. Does that answer the question?
Yeah, thanks.
Great. Thanks for that. Any other questions? So Valentin, I have I guess a question and a comment, and I just want to say that your work is really important for some really key things from my perspective. I mean, I remember working with the Deep Carbon Observatory folks on, well, deep carbon cycling on the planet at rifts, at mantle plume locations. And so one of the things we were grappling with is like, well, why the heck did the Siberian traps trigger a huge mass extinction, the worst one, whereas like your Ontong, Java, Hikurangi, Manihiki superlip in the Pacific didn't actually, I mean, it probably triggered some anoxic events in the ocean, but not a mass extinction. So I think that that's one of the key things why your work is important. And the other one is that in the East African Rift system, people take the carbon outgassing measurements there and they say, okay, all rifts output that much carbon. But I think I have a bit more of a guarded interpretation, which is that the plume is interacting with cratons, cratonic lithosphere, craton edges, and liberating and bringing up huge amounts of carbon that, you know, you probably don't get in like the Baikal Rift, for example. Maybe, I don't know. I just wanted to get your thoughts on any of this. What you think, if it's worth extrapolating the East African Rift, you know, model to all rifts everywhere in the world.
Yeah, so one thing first, you mentioned the Ontong Java plateau, and I think that is something different than what we observe here. We really separate this because it was never linked to a rifting event. So probably it's the same mechanism behind like a mantle plume, but then all of these things of incorporation of continental material, this is something different. And yes, that also has an implication for the environment, because it means for a rifted magmatic plateau, that's probably happening offshore, above sea level, and this oceanic magmatic plateau, then that might happen underwater. So I don't know whether that can make a difference. I've not studied this at all. For the question of what it means, the plume and the rifts and so on, I think that one thing that we learned with the East African Rift system and the Afar region is that we should not take for granted what we think we know. Because if you look deeper into it, until a few years ago, people were thinking that the most evolved part was the northern part. And in fact, the southern part experienced much more extension. And so I think we have to discover a lot of things, and we don't understand. And for example, everybody that calculated volume of magmatic material, they always took like, okay, seawater dipping reflector, this is magmatic material, and I see this reflector below underplated magmatic material. But actually, like what Pauline Chenin, and also there's this paper by Julie Tugend, what they showed is that actually you can interpret this in several different ways. And actually, we don't have that much of a good idea of the volume of magmatic material that is produced along these margins. And that has big implication, for example, for the carbon cycle, because that can change a lot by order of magnitudes, the amount of magmatic material that you produce. So I think we're not there yet to understand really the complexity of all this thing. And when you look, for example, at the Iberian Newfoundland margin, there is something completely different with much less magmatism. And I think it's a continuum between something like future rifted oceanic magmatic plateau, a normal magma reach margin, some in which the seawater dipping reflector have a locked off magma, some like the Danakil where they have not a lot. And by the way, it's surprising because it's so close to the oceanic plateau, it's so close to the plume, but there's not that much magma, at least until recent time, because nowadays there's a lot of magma in the Artel range. Is it a short-lived feature? Is it that it increased a lot? This we don't know. And then you have the intermediate margins and then the magma pool. So I think it's too simple to just extrapolate. Like it was extrapolated, like they drilled one set of or two sets or three sets of seawater dipping reflector and saying that's all the same for all seawater dipping reflector. No, we realize we have to investigate each study site in more details to really know what it's all about.
Yeah, look, that helps. I mean, yeah, so if you assume that all rifts are like the East African rift system, then the contribution is like 60% or more of the global carbon degassing is from rifts. And I mean, you know, you've got subduction zones and other environments as well. But yeah, okay.
The East African rift system is also very much linked with the Afar plume, which is probably one of the strongest around the world now. And you have tons of rifts that are very different. They have different velocity. The East African rift system is also a very slow system. It's 5 millimeters per year in the northern part in the Afar, but in the south it goes down to nothing because you have the Euler pore further south. So that might be also very different to some other rifts around the world and throughout Earth history.
But okay, just on this, because you do mention the Afar plume, and I think that's interesting what you mentioned. Do you think that like the first arrival of the Afar plume, which would have had a huge plume head, that generated huge volumes of volcanism, maybe, and now that there's maybe more limited volcanic supply from the conduit of the plume, I mean, I don't know.
Yeah, that's the model that you currently have in the literature, is that the flood basalts were the plume head, and now you have the plume tail. But now it's more concentrated, but you still have to explain this thick central Afar. You still need the production of much more magma than a normal rifted margin. So it's still more than normal, but less than before. And I think this is something that you could expect from a plume, and then you have the head of the plume and so on. But it's still more than normal, but maybe less than before. There is also a pulse in the that was the Pleistocene, maybe Pliocene, Pleistocene. There was again a pulse with more production. So it's something that is changing over time.
Yeah. But well, the last thing I'll say is that I'm glad you'll be back in Eastern Australia in mid-January. Because I mean, like we don't have a rift, or we had a rift in the Cretaceous, but we still have some really weird volcanics, right? We have the Cosgrove tract that looks like it's related to maybe a continental hotspot trail, but then we have younger basaltic things that are probably not as age progressive. So I think what you're also touching on here, and even on your map here, is that like volcanism in these sorts of settings is it's not like the textbook examples are, you know, there's just a hotspot and you get volcanism just that way.
Yeah, in the literature, there's also a lot of debate about whether there are one plume or two plumes. At depth, there is this African super plume, but then some say that if I have the laser pointer, do you see it? Yes.
Yeah.
That would be a plume, that would be a second one. And now you see all these recent volcanic fields here in Saudi Arabia. This, they could see that it's a channeling of the plume that is bended towards the north and flow under the crust there. So you have, it's more complex than just a single conduit, and that's